Hello everyone. In this video, I will be trying my best to explain how I managed to make my ocean system go from this to this. The journey is complicated, to say the least, so let's get started. To start things off, we will be generating our ocean mesh. We will be using editable meshes for this, so make sure you have it enabled. If it won't let you enable it, then you need to verify your age because, well, Roblox. Our mesh is just going to be a plane that's just really detailed. There are two methods we can use to get the plane we want. One is to hop inside a Blender and add a plane, then subdivide it as much as we want, or we can generate it ourselves, all inside of Studio. I have opted to generate it all inside of Studio just to keep everything together. In order to generate it inside of Studio, we need to break the mesh down into its separate components. We have vertices, normals, colors, UVs, and the triangles. We're going to start off by generating all the vertices we need. In this example, I have a grid of 5 by 5 vertices. The neat thing about generating a plane though is that everything is actually super easy to compute, as the UVs are just the coordinates of the vertices but normalized. So instead of ranging from say 0, 0 to 4, 4, they would instead range from 0, 0 to 1, 1. The way you normalize the coordinates though is by taking every point and dividing both components that make it up, x and y, by the length of the axis they are on respectively. For example, if I took point 1, 3 on my grid and wanted to calculate the UV, I would divide each number by 5 minus 1. So my UV would end up being 0.25, 0.75. The normals for a plane all point directly up, and the colors we can default to white. Nothing too crazy here. The hardest part by far is going to be the triangulation process. So first, let's start with this basic quad, and hopefully you can see how the pattern repeats from here. So we start off at point 0, 0 and draw a line from here to point 1, 0. Let's now draw a line from here to the point above it at 1, 1. If we then draw a line from our third point back to our first point, we can see our first triangle. Repeating this step once more for the points on the other side gives us a quad. One thing you have to worry about on this step though is something called the winding order. Messing this up and you will get triangles that end up facing downward instead of upward. With our mesh data complete, we now have the ability to spawn however many meshes we want, all referencing our single editable mesh. This means a single change to our editable mesh will affect all meshes created using its content, allowing for an infinite tiling ocean while only using up a single tile's worth of resources. Since we now have our mesh, next step is to create our material. Generating the material is a little complicated as we need 4 different types of maps. If you've done any modeling or used any PBR materials before, you can already guess which ones I'm talking about. Normal, roughness, color, and metal. Since we're going to need to change these different maps at runtime, we need them all in the form of editable images. Thankfully, Roblox has a beta feature that you can enable where you can set the different maps of surface appearances to be that of editable image content. With this being the case, we can generate each of the 4 different maps as editable images with the same resolution as our mesh. You'll want 2 different coloring methods. One, which colors the entire image a single color, and another that allows you to change the color of each pixel. Since our roughness and metal maps will just be solid colors, the single color method is all you'll need for those. Now, to keep things organized, instead of having a bunch of loose editable images stored in a table somewhere, I'm going to create another class which takes in 4 editable images and call my custom object a material. This is just so that I can create a method attached to this class to make it super easy to generate a new surface appearance from the already existing editable images I made. With all this done, we can now parent the surface appearance to a brand new mesh, and there we are. We now have the ability to draw a runtime created texture on our runtime created mesh. Now, to test everything is working properly, let's color the pixels on each of our corners a new color. Top left will make black, top right will make red, bottom left will make blue, and bottom right will make green. Something you will notice is that it draws the pixels correctly on the mesh, however, you can see that the corners are not completely filled in. This is because a vertex and a pixel exist in two completely different places, despite having a similar local position. To show you what I mean by this, let me show you a wireframe version of our grid. We can start by marking all our vertices with red dots and all of our pixels with blue dots. Notice something? They aren't aligned. This is because vertices technically exist at the corners of our pixels, meaning there is a very minor offset in their two locations. This can be fixed by offsetting the origin of the UV by 0.5 on each axis, making it so pixel 0, 0 lies exactly on the vertex located at 0, 0. Now that we have built the foundation for actually visualizing our ocean, let's start getting into the brains of the system. Now that we can both create our mesh and generate PBR textures in real time, we need to know what to do with each. The mesh is what's going to make our ocean actually move physically, and the material is what's going to add things like color and lighting to our ocean. But how do we know where to move each vertex, or what color to make each pixel? Well, that's where our ocean spectrum comes into play. Our ocean spectrum is going to be what defines our entire ocean. Different ocean spectrums will give vastly different oceans. An ocean spectrum defines all the frequencies our ocean has within it, and also the amount of energy given to each of those frequencies. Typically, when you construct an ocean, you think of waves as how wide and tall they are, or to be more precise, their wavelength and amplitude. This way of thinking of the ocean is standard and makes the most sense to us. A more technical way to describe this is thinking of the ocean in the time domain. However, our ocean spectrum is actually in the frequency domain. The reason we generate our ocean using the frequency domain rather than the time domain is actually for simplicity. If we were to construct our ocean entirely in the time domain from the start, we would have to manually input possibly thousands of waves, which isn't very scalable. However, if we generate the waves in the frequency domain, we can simply input the frequency we want into our spectrum and we instantly get back the energy for our wave. Knowing the amount of energy being put into our wave is key, as we can then directly solve for our amplitude using this formula. Our ocean spectrum is also going to be based off of real-world ocean data, meaning not only do we get an easier and faster method for generating our waves, but it's also going to be more physically accurate. Something pretty neat that I discovered while doing research is something called Hermitian symmetry. For our IFFT to output real numbers, which we need since we are working with physical heights, every frequency in our spectrum requires the same frequency at the mirrored position with its imaginary component flipped. We can make the process of getting these mirrors quick and easy by pre-computing them alongside the original spectrum generation. We are placing them inside of the generation itself since the relationship between a frequency and its mirror never actually changes. After generating our spectrum, we now need to evolve it to give movement to our water. When I say evolve our wave, I need to specify that our wave in this case is just a rotation. The height of each wave is oscillating between -1 and 1, similar to a sine wave. This is exactly what a point spinning around the complex plane looks like. Think of it like looking at a point moving on the surface of a circle, but you are viewing the circle from the side, so it would appear as a line. The point is going to appear to bounce from end to end on the line. Left to right, -1 to 1. In order to actually evolve our spectrum though, we need to take a look at Euler's formula. Omega in this equation is our wave's dispersion frequency. We can solve for omega by using the wave vector. This is what makes our waves with larger wavelengths, lower frequency, travel faster than those with shorter wavelengths, higher frequency. Multiplying a complex number, which is two numbers, real and imaginary, by that gives you a new real and imaginary component to a new complex number. If we assume the real part is A and the complex part is B, you get this. When you multiply a complex number by I, you are technically rotating in the complex plane by 90 degrees. This is also what we use to derive both the horizontal displacement and also our normals. However, this is only part of the formula. The full implementation looks like this. The second part here actually isn't doing anything physical. It's actually more like bookkeeping. Its existence is so that when we eventually pass our result into our inverse fast Fourier transform algorithm, we get real numbers that we can actually use. After evolving our spectrum, we now need to convert our frequency domain representation into the spatial domain so that we can actually see our ocean. The algorithm we are going to be using is called a Fourier transform. There are different types of this algorithm, but the one that's meaningful to us is called the fast Fourier transform. The reason we are using this one over the more well-known discrete Fourier transform is simply due to time complexity. DFT has a time complexity of O of n squared, whereas the FFT has a time complexity of O of n log n. The forward fast Fourier transform is an algorithm which takes a complete signal and breaks it down into the frequencies that make it up. You can imagine how this is useful by looking at it from an audio perspective. This algorithm can be used to make things such as low and high pass filters. This is nice and all, but the version we are looking for is actually the inverse fast Fourier transform, which, rather than breaking an already combined signal up into pieces, it takes those pieces and combines them all into a single signal, which we then use to displace our mesh. This inverse fast Fourier transform that we are using actually has multiple different implementations, and the one I'm choosing to use is one called the Radix 4 Stockham. Typically, with IFFT algorithms, you need a final pass at the end called a bit reversal, which adds complexity and computation time to the entire process. However, using the Stockham approach, you can completely avoid this step by ping-ponging your data between two separate storage containers as you are processing it. The Radix 4 part of the name just represents how many operations we are doing at one time. Explaining every step of the algorithm is outside the scope of this video, so if you're interested in how it works, there are plenty of resources on YouTube that do a way better job than I could. At this point in the process, we have everything we need to begin rendering our final result. We have easy access to the displacement at any vertex because our mesh is perfectly aligned with our FFT resolution, which is also perfectly aligned with our texture resolution. We can sample all three displacement values per vertex, x, y, and z, and convert from world space to object space, giving us our physical movement for the ocean. Next, we can choose whichever coloring method we want to use for the water. The one I recommend, which makes things easy, is a simple blend between three colors based on the vertical displacement of the vertex. The higher the vertex, the lighter and more green we can make the color, and the lower the vertex, the darker and more blue we can make the color. We make the peaks of the water more green tinted due to an effect called subsurface scattering. And because water reflects mostly blue light, the blue water, mixed with the yellow color of the sun, results in a greenish hue where the waves are highest and most susceptible to scattered light bouncing out. We can also construct our normals using the derivative values we computed and generate a color in tangent space, where our y-axis is represented in the blue channel, the x-axis is represented in the red channel, and the z-axis is our green channel. A normal pointing directly upwards ends up coming out as 0.5, 0.51 in normalized RGB space. The reason a normal of 0, 1, 0 ends up as 0.5, 0.51 after conversion is because normals on each axis can range from -1 to 1, but our colors range from 0 to 1 for each channel, so they end up requiring remapping. If you are too lazy to figure out the normal to tangent space color conversion, here it is. And to go with it, here is the three-way color blend. After everything is said and done, you should now have a beautiful ocean that you can do whatever you want with. The way it looks is going to heavily depend on the ocean spectrum function you are using. My implementation is using the Phillips spectrum, so I only get one parameter to play with. However, if you decide to use a different spectrum, such as the John swap, you can get a much more realistic and controllable ocean. With that said, the ocean you just made isn't really useful if it doesn't run well. And since this is meant to be used for games, we need to be using every optimization strategy we possibly can. Unfortunately, I will not be going over my own code implementation of this, as it would take far too long and is too complex to explain every single detail. But what I can show is the benchmarks of my own system. Benchmarking is something you should be doing for every system you make, simply because if your game runs like shit, then nobody is going to be able to play it. The benchmarking I did was in two separate parts, the cascade updating stage and the render updating stage. The cascade updating stage encapsulates the entire ocean spectrum evolution alongside everything up to and including the inverse fast Fourier transforms. That time came out to 0.001485 seconds, or 1.485 milliseconds. The render updating stage encapsulates the entire ocean visualization, everything from moving the mesh to the coloring of every texture. That time came to 0.000712 seconds, or 0.712 milliseconds. For reference, if you were running your game at 60 frames per second, each frame lasts about 16.67 milliseconds before showing you the next one. These results mean that I can safely run my ocean at over 500 times per second, aka 500 FPS. But the reality is that I would be dedicating way too many resources just to rendering water, which from a game development standpoint is a crime. So I chose to limit my ocean to update at a reduced rate of 24 frames per second, allowing for more resources to be devoted to the rest of the gameplay mechanics. If you are too lazy to build the entire thing yourself and you also want to support me, you can check out my fully optimized and game-ready implementation in the description. I hope this video helped you understand just how much work can go into something as simple as water. Anyway, I need to go find something else to waste my time on and make another video about. Goodbye for now.